All right, so section 5.2 is on sigma notation and the limits of finite sums. So if you haven't got homework started yet, I would encourage you to do so just so you're comfortable with the ideas as we continue to build them up. In this section, we will develop notation to evaluate sums involving many terms. So if you notice, we had a lot of terms last class. If you even look at this one right here, I even got lazy and cheated and just did so on, follow this pattern. So it'd be nice to have some sort of notation that basically consolidates all of this writing into something that's a little bit more manageable. And that's what sigma notation is going to do. So after developing this notation and some of its basic properties, we will consider what happens to the number of terms or as the number of terms approach infinity. So basically when we let those rectangles get really small, that's what we're going to do once we have this notation. So so you know that phrase is all Greek to me. Well, that's literally what we're going to be talking about is something that's just Greek, but it is going to have a notation. That's just a notation. So the Greek letter, this one right here, it looks like an E, but it's actually the capital Greek letter for sigma, and this corresponds to our letter S, standing for sum. So we're going to just do a few examples of this one right here. This first one, what we're going to have is the sum of k as k goes from 1 up to 5. So, and we'll kind of look at what this means down here below in terms of like the terminology, but you can think of k as like a sort of formula that you're going to plug the numbers 1 to 5 into, and then you're just going to go ahead and add them together. So we're going to start with k equal to 1. So the summation is the first one. So this is right here where k was equal to 1. So notice that this is, just imagine like I plugged in k, or x is what we're used to plugging into. Then the summation means I'm going to plug in 2. So this is the scenario where k is equal to 2. Then I'll plug in 3. Then I'll plug in 4. And then I'll plug in 5. So that notation right here at the beginning just means add 1 plus 2 plus 3 plus 4 plus 5. And when you add those together, you end up with 15. On the second one, our formula is a little bit more involved, is k squared. And we're starting at 2 and we're ending at 4. And again, we're just using integer values here. So the first thing I'm going to plug in 2 and I'm going to square this. So this is where k was equal to 2. Then I will add to that 3 squared. And notice this is where k is equal to 3. And then lastly, I will plug in 4 squared, and this is where k is equal to 4, my ending index. So when we add this together, we get 4 plus 9 plus 16, which is ultimately just going to be 29. Any questions on the first two? So k just is a placeholder letter. You really have some options. Typically, we'll use either k or I or j. And especially for those of you going on eventually like Calc 3, I, J, K are typically your 3 kind of indices for moving through 3 dimensions. But you see an example here, instead of K, we're using I. So we're going to let I go from 1 to 5. And this is the formula we're going to plug each I into, and then we'll add them together. So this one is going to be a -1. Then I'm going to plug in I equal to 1, so that's right there. Then I'll go -1, and I'm going to plug in I equal to 2. That's going to go right there. So this is where I is equal to 1. This is where I is equal to 2. And then I'll add -1, and then this time I is equal to 3. So this is again where I is equal to 3. And then we have plus -1, and then we have I is equal to 4. So I'm going to plug in 4 right there. And then lastly, I have -1 to the 5th. So is everyone okay with where we got all of those 5 terms and added them together? So of course, we could simplify this. The first one is going to be -1. The second one's positive, then negative, then positive, then negative. So -1, +1, -1. So this works out to just be -1 as the sum. So this is a nice little kind of pattern to store in your head, because this -1 to the variable or whatever letter we're using to iterate through, this allows us to alternate between plus or minus. Any questions on that one? Okay. And then number 4, this one's interesting because there is no variable. There's this is not 3i, and again our index here is I. So this basically just means there's nothing to plug in. So what we're going to do here is add 3 to itself for each index. So the first one is going to be 3. This is when I is equal to 1, but notice there's no I there, so there's nothing to plug in. Then we'll add to this a 3, and this is where I is equal to 2. Again, there's no I there, so we have nothing to plug in. And then we add 3 right here, and this is where I is equal to 3. So what we'll end up with right here is simply 9. Any questions on this one, on these 4 examples? Yeah, Destiny.
So just for number 4, so then, if there's no variable in play, where that 3 is, you just added the amount of times as you would the other ones?
Yes. Okay. Yeah. And you might notice right here, it's something maybe just to plant a seed, you might notice that this 9 is just simply 3 times 3. Okay. So those are some nice patterns that will help us as we go through this. Maybe just let me give you one more example just to see if the idea is stuck. So let me also go ahead and just do a 4b right here. And let's say this is going to introduce something a little bit different, but I think you're going to be able to extend it pretty well. So let's let k run from 1 to 3. But let me give you a scenario where you have multiple inputs. So -1 to the k times k. So let me give you a moment to see if you can go ahead and answer this one. What is the sum from k equal 1 to 3 of -1 to the k times k? And once you think you have your answer, if you flip to the next page, you will see the answer on the next page. So on the next page, you have 4 extra examples. I asked you to do the second one right there. So notice that is pretty straightforward. Same principle, except for you have 2 different scenarios where you plug in, because there's a k in the exponent and a k in front. So notice that as we iterate from 1 to 3, there are 2 inputs as you sum them together. How many got the answer of -2? Many of you. Very good. See, I told you, all we're going to be doing for the next chapter is adding. So we're going to build up the ideas, and keep in mind, we're going to be talking about area under the curve. Does anyone have any questions so far? Okay, so let's slide back up to the first page, and I just want to make sure we have kind of the terminology written somewhere for reference. So as I refer to certain words, you know kind of what I'm talking about. So this big symbol right here is the Greek letter S, capital S for sum. So this right here is just the summation symbol. So this right here is the summation symbol. Then the k equal to 1, if you notice, I've been saying the phrase index. So the index is the k here. So the index k starts at k equal to 1. It does not need to start at k equal to 1. As we'll see, it could start at negative numbers. It could start at positive numbers. It could start at 0. But it will iterate through the integers or counting numbers. So then the n at the top, the index k, ends at k equal to n. So that's the last number we'll plug in. And then a to the k right here, this is a formula for the kth term. So this is a formula for the kth term. So if it was 1, it would be a formula for the first term where you would plug in like 1 for k. If it was like k was 3, it would be the formula for the third term where you plug in 3 for k and so on. So in general, you could expand summation notation as just a sub 1 plus a sub 2 plus a sub 3 plus so on. So again, remember ellipses. Technically, they're not ellipses because they're actually in the middle. So on up to a n minus 1 plus a to the n. So this is, let me just kind of call out what we're looking at here. If you follow this pattern, like right before you get to the n, you're at 1 less than n. So that's why you have n minus 1. So that is our summation notation. Let's go ahead and kind of go the other direction now and suppose that we're getting a sum and we need to go ahead and actually write the actual formula for it. So if we look at these next few examples, 5 and 6, we're asked to express the sum already given to us in sigma notation or summation notation. So this first example, what we're doing is we're going to sum the odd numbers. So sum odd numbers from 1 to 9. This is, again, will take some practice because you have to think about, okay, what numbers or what formula as I plug numbers into generate this pattern. So there are certain things to hold on to, like that -1 to the I or -1 to the k allows us to alternate signs. This one is a good way to represent odd numbers. So a good way to represent an odd number is just using something like 2 to the k plus 1. And again, if you think about it, what is an odd number but an even number that has 1 increased by it? It doesn't have to be 1. It could be 3. It could be 5. But to get an odd number, you're going to take an even number and realize what is every even number divisible by? 2. Hence, the 2k gives you the even number, plus 1 is going to move you to an odd number. So with that in mind, let me see if you could take a moment to write a formula in sigma notation, because now you have to think about indices. But let me give you maybe about 20 seconds to see if you could answer this right here. All right. Anyone think they have it? Let's go to Luke first, actually, today. So you're going from k equal to 0 to 4. 2k plus 1 is your formula. So let's check this. So if you plug in 2 times 0 plus 1, this is where k is equal to 0. Then you have 2 times 1 plus 1. Then this is where k is equal to 1, and then you have plus 2k plus 2 times 2 plus 1. So that's where k is equal to 2, and then finally 2 times 3 plus 1. So this is 1, 3, 5, 7, and you went to 4, so why 2 times 4 plus 1? This is good. And Destiny, did you get the same thing? Very good. Notice here the index started at 0. That's fine. You're just going to have your indices start at some integer, positive or negative. And this does work if you choose to use 2 to the or 2k plus 1. Thing to note, this is not the only answer. So what if you were to consider using the formula k minus 1? What would your indices be in that case? Where would you start? Where would you end? If you think you know, Weston?
1.
This is where you start at 1 and you would go to 5. Yeah. And again, there's infinitely many answers to this one because you just have to, like, if this were 3, then you would just have to adjust this up to 2 and then this up to 6. So again, it's just one of those things. You have some flexibility in the choice of our summations based off of our indices. And there are some nice tricks with the indices as we go through. We'll understand most of them in Calc 1. We're going to keep fairly basic. But for those of you who go in Calc 2, definitely start to grab onto these ideas and think about the different manipulations you can do by just shifting indices. Any questions on this one? Okay, so again, in number 2, we're going to have the sum of the even numbers. So we're going to sum even numbers from 2 to 10. And even numbers typically could be easily represented by just the formula 2k. Because I think Caleb, you answered, every even number is divisible by 2. So if you take any number k and you double it, whether it's even or odd, is now going to be even. So with that in mind, go ahead and take a shot at that one. And just to see if the ideas are sticking, let's go ahead and also throw up here for fun 6b, which I will have as, let's say, 2 minus 4 plus 6 minus 8 plus 10 minus 12. So go ahead and try 6 and 6b, where I just made up 6b on the spot, so I'm going to have to think about that one for a moment too. But we do have the skills to get it at this point. All right, let's see how we did. So let me ask, anyone think they got number 6? I heard from you, Luke. Let's see. Roxana, you think you know it? Want to take a shot? Okay. What do you think? K equal to 1? Goes to 5 and 2k. So that looks good. Do we have a second on that one? Yep, got your peers behind you nodding. Very good. This is correct. You could confirm it if you would like, just by doing like 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus the final index 2 times 5 does give you 2 plus 4 plus 6 plus 8 plus 10. Very good. Anyone have any questions on number 6? Okay, 6b a little bit trickier. Let's see, does anyone think they know the answer to 6b? Destiny, you want to give it a try?
I'm kind of scared.
Give it a try.
I kind of used the variable x to solve, and I factored out each of the 2. So I got 2 parentheses x minus 2. So I'm guessing it's 2 parentheses 2k minus 2.
Hold on, say that again.
Sorry, 2 parentheses k minus 2.
K minus 2 parentheses right here. And what were your indices?
I didn't get that far.
Didn't get that far.
I would probably guess like 5. I guess it would go to.
Well, yeah. Let's. A lot of these you're just gonna have to experiment with, and again, some of these are not obvious. So let's start simple. Let's start with let's say like 1. If I were to plug in 1 here, I would get 2 times 1 minus 2, which would give you a minus 2. Okay, well, I'm off a little bit, but it's kind of the right thing. So let me see if I start, what if I start at 2? If I started at 2, this is going to be 2 times 2 minus 2, which is going to give me 0, so that's not going to work. So let's try starting at 3. If I do that, we're going to get 2 times, so maybe 3. So if I do 2 times 3 minus 2, that would give me 2. But let's see what would happen if I tried when I did 4. I would have 2 times 4 minus 2, which is going to end up giving me, oh man, the sign's off. Do we have a way to alternate signs though? Savannah, you're nodding your head.
If you multiplied a negative by a positive,
So we need some multiplication by a negative. So let me maybe slide this over. And what we could do is, let's say we add a negative 1 to the, didn't want to get rid of all that. Let's say a negative 1 to the k here, and let's see what that does. So if we were to multiply this by negative 1 to the k, let's see, we would have negative 1. Let me make my pen smaller here. So let's make equal here. So if we did this, you would have negative 1 to the third. Ooh, that would be negative. So, but then this one would be positive. So we're almost there if you kind of look at this. We're just starting with the negative in the wrong spot. So any ideas? What's one more thing that we need to go ahead and do to adjust this to be the correct formula? Destiny, you want to see if you
K negative?
we could, if we did k negative, let's see what happens. That's not what I was thinking, but it might work. Like I said, there's multiple answers. So if I did that, no, I wouldn't want k negative, because that's what happens if you would start getting like a 1 over. Because, let's try it. So if I did this, I would get negative 1 to the minus 3. Would that actually work? It might actually work, because it's still going to give you a negative. No, the issue is the 3 is odd. The issue is the 3 is odd. Savannah, I think you had an idea.
K plus 1.
Let's just add 1 to it, because we just have the wrong parity, or not the parity, the wrong even oddness. So we don't want to just do the negative k, we want k plus 1. Because if you do k plus 1, this is now 4, which makes this a positive. This is now going to be a minus, so this is going to be a minus 1 to the 5, because this is where k is equal to 4 here. So that's now going to make this a minus 4. So here we have an answer. Maybe not the simplest one, because you have a lot going on with the multiplication, but good work, everyone. We have a formula. What is our ending index? How many numbers? So we have 1, 2, 3, 4, 5, 6. So if we start at 3, how high do we have to go? Emma? I think 9. I have to think through this. So 3, 4, 5, 6, 7, 8. Yeah, because you include that starting index. So it is just going to be up to 8, because you include your starting index at 3. So yeah, that we worked there. Again, this is one possible answer. The one I had in mind as I wrote this was k starting at 1, going up to 5, going up to 6. And then having just 2, then I would have minus 1 to the k plus 1 times 2k. You just kind of did a shift of mine, Destiny, by because basically what you're doing here, if you distribute it, yours is just 4 less than mine. So you still have that same property of multiplying by 2 makes it even, and negatives with the input and the exponent allows you to alternate. So again, a little different, but still valid, very good. Anyone have any questions on 6b or 6 or anything so far? Just adding, right? Let's just keep it just adding. All right, so now that we have the basic ideas down, we want to see if we can maybe start developing shortcuts. Shortcuts are nice. It's kind of like, when we were doing derivatives, we had the whole limit thing we had, and then we finally learned about the derivative rules and oh yeah, limits are fun. So it's the same principle where we have the notation, we want some rules for it, so we could start shortcutting some of the thought processes and kind of just storing those patterns in some nice simple rules. So we have some rules right here. So these are just basic algebraic rules, and if you think about them, they're pretty intuitive. If you have a formula that involves a sum, you can just go ahead and just consider each part of the sum independently. If you think about it, this would be why is this one true? Because you can move things around as you add. You can, if you have 2 plus 4 plus 6, you can do this as same as 2 plus 6 plus 4. So if you think about it, this is just a bunch of addition. We're just moving around. So this is pretty natural. Same thing with differences. This is nice, this constant multiple rule. If you have a formula with a constant, you can just move that constant out in front. And then this constant value rule, if there's no sort of variable to plug things into, you just multiply the top index by whatever the number there is. And I think we kind of alluded to that one earlier. So just to see how these rules play out, again, this one is just an illustration of the rule because we don't have a number. We're just saying n is up here. So this is the scenario where what we can do is you can see here's the constant multiple rule. So if I could bring this 3 out front, and I could still consider the sum from k equal 1 to n of k. And then you can see it's not technically distribution, but you can imagine the sigma could affect each part of the difference separately. So then you would have a minus. Let me just do it with this. Sometimes my colors just throw up on the page, but then you could go ahead and consider this separate one, k equal 1 to n of k squared. So instead of plugging everything into that bigger formula, you could go ahead and separate it kind of with just basic properties of addition and subtraction and multiplication. Everyone see where we got that? Because what's really going to be nice is we're going to have some nice formulas for these basic ones. So instead of having to plug in things, we could actually just make a substitution where something is not a sum. So number 8, by the way, is always nice to just realize that we can pull this negative out front. And this is just going to be the same thing as minus the sum of k equal to 1 to the n of some formula a sub k. And this is natural. You could always factor out negatives if there's from all terms. So that's what's happening here. You're factoring out a negative. This one we could go ahead and compute fairly straightforward. Instead of dealing with that plus 4, what I can do is I can consider the sum from k equal 1 to 3 of k. And then I could go ahead and consider the sum from k equal 1 up to 3 of 4. We could simplify this pretty easily, though. I mean, this first one's pretty straightforward to do. 1 plus 2 plus 3. But notice that this is just going to be a constant here. There's no variable or index that's moving and iterating through here. So why did I highlight 3 and 4 is because to figure out that second summation, what do you simply have to do? Multiply 3 times 4. So it's going to be plus the top index times 4. Now this is working under the assumption, if you look at this, this is working under the assumption that k is equal to 1. So this is kind of, maybe just kind of emphasizing this, that this is, we are kind of doing this under the assumption, assuming we start at k equal to 1. If it's not 1, you kind of just have to, do you remember earlier how I said, when Emma mentioned 9, I'm like, hold on, I have to think. I'm like, 3, 4, 5, 6, 7, 8. I kind of did the counting. So really, it doesn't matter what the bottom index is. You just have to think of how many times you're adding. So like if that was k equal to 2, then you would just do 2 times 4. If it was k equal to 3 and still went to 3, you would just do 4 because it would just be the one index. So that's kind of a little kind of underlying assumption. And number 10, if we look at this, we want to be really careful. What is the index in number 10? Look at the bottom. The index in this case is k. Do we have a k in our formula? No. So this one is just literally going to again be n, not 2, n times 1 over n. It's that same constant value rule. So be careful because we kind of have two variables in mind here, like n is a number we could plug in for, but our index for the summation here is going to be k. Since there's no k here, it's just the answer is going to be 1. If you wanted to, you really are doing this as like 1 over n plus 1 over n plus so on plus 1 over n, where this is occurring n times. So that's kind of the expansion of that. But if you do add 1 over n to itself n times, you end up with just 1. So any questions on this one? All right. So what we want to do next is work with getting some formulas for like these common ones. And let's look at this right here on the next page. So number 11, one such puzzle associated with sigma notation is finding a formula to evaluate the sum without writing out each term. It would be nice if we can just say, oh, look, our starting index is 1, our ending index is 10. I just am going to plug 10 into some formula. Find a formula for the sum of the first n positive integers. So what we're going to do is we're asked to find a formula for this. So we're wanting to find a formula from k equal to 1 to n of k, and we're going to find some sort of formula that we can just plug in numbers. By the way, this formula was supposedly found by Gauss at age 8. Show off. Gauss, again, is a historical mathematician. Can't remember the exact time frame, but his influences on many current branches of mathematics. So I don't know if the story goes, but Gauss is smarty pants, distracting the class. So the teacher's like, hey, I have a formula or I have a challenge for you. So the teacher's like, go over there, try this, quit being such distracting Gauss. And he's like, go ahead and find a formula or find the sum of the first n positive integers, or let's say he asked Gauss to do the first 200 positive integers. At 8-year-old, I wasn't going to add 200 positive integers. It's like, 1 plus 1 is 2. No, it's not. Yeah, or 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. It's going to take him a little while. So Gauss comes back like 20 seconds later, and he's done because he figured out this formula. So let's figure out, so this is some of the reasoning for the formula, and it's really kind of clever. So instead of adding all of these numbers, imagine you just add 1 plus 2, 1 plus 2 plus 3 plus so on up to n. So let's also include n minus 1 plus n. So let's suppose again, that's what we were asked to do. Add the numbers from 1 up to n. Here's the clever thing that he figured out. Go ahead and also, if you were to add them backwards, what you end up with is you would have n here, you would have an n minus 1 here, you would have an n minus 2 here, so on. You'd end up with 2 here, and then you'd end up with 1 here. Do you agree that those are the same number, just one you're adding forward, one you're adding backwards? So this is where it gets clever. If you think about this, what we have here, what happened here? Let me do this. Let's go ahead and just add the columns. If you add the column, what do you get in each column? N plus 1. What do you get in the second column? N plus 1, N plus 1, N plus 1, N plus 1. So this is the clever thing here when you get this formula. What we have is N copies of N plus 1. Right? Does everyone agree with that statement? We have N copies of N plus 1. So what is this? In green, we have N copies of N plus 1. What's this in red? We have 2 times what we were asked to find, k equal 1 to n. So if you solve that for the sum, the formula is n times n plus 1 divided by 2. So if you just divide both sides here by 2, you get the formula. So suppose that you want to go ahead and, well, let's kind of look at this in terms of an example. Suppose you want to go ahead and add k equal the 1 up to, let's say 20. The first 20 terms. What does it add to? Well, you can do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, so on. I could have already had the answer using this formula. What is n? N is the top index. So this is going to be 20 times 21 divided by 2, which is going to be 10 times 21, or 210. So that is a short formula to go ahead and add the first 20 numbers, positive 20 numbers. So just to make sure you're okay, k equal, let's say 1 to 11 of the first, that's 11. Wow, my sigmas are getting bad. Let's clean that up. So what would be the sum of the first 11 terms? Once you got it, just shout it out. Or talk it. You don't need to shout. It's okay. We have a 66. Do we have a second? It would be the 11 times 11 plus 1 divided by 2, which is 11 times 12 divided by 2, which is 11 times 6, which indeed is 66. Very good. So that is the formula for the first n positive integers being added together. Any questions there? Okay. So you also have 2 formulas down here for the first n squares and for the first n cubes. Say again, question, Destiny, you have a question? I'll get the word out correct, or words out correctly.
I'm so sorry.
Sure.
Where did the 11 come from and the 11 times 6?
Sure. So this formula right here, up here, whenever you're asked to find the sum of the first n being how many is your top index, where does your index end? So this is going to be n times n plus 1 divided by 2. So n is your ending index, or where your index ends. So in this case, we end at 20. So this is going to be 20 times 20 plus 1, which is 21, divided by 2. In the case here, n, this n is equal to 11. Here, n is equal to 20. So this is going to be n plus 1. And then n plus 1 is 12, and then 12 divided by 2 is 6.
Oh, so we don't divide n by 2 then?
It doesn't matter. In the first case, I divided n by 2 because it was the even number. In the second case, I divided the n plus 1 by 2 because that was the even number. One of them are going to be even. So it's always going to be nice to simplify that.
Oh, so you only have to divide.
Yes. This is an addition. It's either the first number or the second number will be divided by 2. Yeah. Addition, you would divide them both by 2, but this is multiplication between 11 and 12.
Okay.
Yeah.
Thank you.
Okay. By the way, for the test, I won't require memorization of these formulas. It's just one of those things. You will need them in Calc 2 because they'll show up a lot. but just to maybe offload some of the ideas so you could kind of get the general ideas. More of a higher level is going to be important for Calc 1. So you won't be required to memorize these 3 formulas, but it's still interesting to see where they came from. Let's now see where they're used. Let me look at how I want to do this. Okay, so I'm going to set this problem up, but I'm going to save the heavy computation to when we're fresh for tomorrow, but I want to set the problem up and kind of explain some terminology. So if we look at this right here, section 5.1, we use rectangles to find and approximate the area under the curve. What happened as the number of rectangles increased and the subintervals became smaller? What happened to our estimate? It became more accurate. Exactly. Very good, Emma. So again, it became more accurate. So if we think about this, what we started with is the scenario where we had the distance of 1/2 or 0.5, well, let's do fractions, 1/2 as the rectangle's width. Then we went to 1/4. Ultimately, what we want to go ahead and do is go ahead and we could end up getting 1/n, where n is just going to be the distance between, or the total, where n is just going to be the number of rectangles. But if we really wanted to go ahead and continue this, what we want is to basically let n go to infinity. So we have the ideas of limits right here. So our width right here, so just to maybe kind of color code this, the width that we're looking at for each rectangle is just some change in x value, which is going to be 1/n for this simple case. And then we're going to let n go to infinity. So for the sake of simplicity, I will want to go ahead and let me just ask this question. The rectangles above, for these estimations above, are we using the upper, lower, or midpoint rule? Up above, we're using the, how many say upper? How many say upper? How many say lower? No one. How many say midpoint? So the correct answer here is upper, because you can see right here that our rectangle is using the maximum right here, the left end point. So it's an overestimate. So it's going to be so this is using the upper. So I'll just kind of write this here. The above uses the upper sum. But I'm going to go ahead and, for the sake of simplicity, we'll carry out this full computation tomorrow, but we will use the lower sum. The reason I want to use the lower sum is because I really want to start at a different index. So how can what I want to do is kind of capture this last piece right here. So the area, if I let n go to infinity, I am using the smallest possible rectangle. So at this point, we're going to use equality because it's not an approximation. If I consider the limit as n goes to infinity. But what do I need to find the limit of? So this is kind of a tie-in from yesterday. I need to go ahead and get basically all of these points right here. So how do I do that? The first one, and I'm going to use the lower sum because what it would allow me to do is to kind of start with 1 instead of 0. So what I'm going to do, the first one is just going to be obtained by plugging 1 into whatever our function is. But then we're going to multiply that by the width, which is just going to be 1/n. Again, this right here is our width. Plus plugging the second in times 1 over n plus so on. You know what? Hold on. Hold on. Okay, hold on. We're not plugging in 2. Careful, let me back up here. We're not going to plug in 2. What we want to do is plug in the second rectangle's x value, which is going to be 2 times the width. So what we'll plug in here is going to be 2 over n. Then what we're going to go ahead and do, if we continue, let's just do another one. So then the third rectangle is going to be at 3 times the width, or 3 over n. And then we're going to go ahead and still have the same width for that rectangle. And if we were to continue doing this, what we would end up with is the last rectangle is f of n over n times the width right here. So that is what we manually did last time, but we have the limit to consider now. So what the next step will be is to go ahead and write what I did above in terms of the sigma notation. So we're going to have the sum from k equal 1 to n of f of k over n times 1 over n. So f, let's just use this function right here. So y is equal to 1 minus x squared. So is everyone okay with where I just wrote that in terms of our sigma notation? Because notice that we're iterating across. So this would have been, so this is 1 over, so hold on. This first one should also be 1 over n, I believe. Sorry about that little typo. That should have been 1 over n. Because you're iterating, we're increasing the top. So there's our k. Notice our width is the same in every single time. So what we're going to go ahead and compute, and this will take us a few steps. I would actually encourage you to try this just to kind of see if you could orient yourself to tomorrow. When we're using our given function, our formula right here is going to be the sum from k equal 1 to n. And then we're going to have 1 minus k over n all squared times 1 over n. So notice that I just took k over n and plugged it in for the x, because that's our function. That will give us the height of the rectangles. Any questions to this point? So this is going to take us, I should have probably written a little bit smaller. So this will probably take us 1, 2, actually 3. So there's about 4.5 intermediate steps. But does anyone remember what the area of that it was yesterday when you used really small rectangles? Grace, I haven't heard from you. It was approximately 2/3, but when we're all said and done, because we're considering arbitrarily small rectangles, it is going to be exactly 2/3. And there's some work to do on that. I'm going to leave this as maybe give it a try tonight to see if you could put together the rules we talked about, but we will go through it tomorrow. Any questions? All right. Have a good day, everyone.